Inside every single machine you can think of, from your car to, well, even a simple sewing machine, there's an invisible war happening right now. It's a battle against this relentless enemy that just generates heat, causes wear, and grinds everything to a halt. So today, we're going to pull back the curtain and see how these unsung heroes, the lubricants, actually win this fight. First, let's meet the enemy. So what is this powerful, unseen enemy? You might be thinking, is it heat? Or maybe pressure? Nope. It's something way more fundamental. Something that exists on any two surfaces that touch each other. The real enemy is friction. And it all starts at a scale you can't even see. And this is where things get really interesting. If you take any two surfaces, even stuff polished to a perfect mirror shine, and you zoom in, like way in with a powerful microscope, you'll see they're not smooth at all. They're actually these rugged little landscapes of microscopic peaks and valleys. The technical term for these peaks is asperities, and these are the frontline soldiers of friction. Okay, so here's the problem, right? When you try to slide one of these surfaces over another, those tiny peaks, those asperities, they literally smash into each other. They interlock, they grind, they even break off. And all of that microscopic clashing, well, that's what we feel as friction. It's what generates all that destructive heat and literally wears the material away, destroying our machines from the inside out. So, how do we fight back? Simple. In this explainer, we're going to look at friction, the unseen problem. Then we'll meet our hero, the lubricant. We'll break down the three main ways they work, and finally, we'll see how we test them to make sure they're actually up for the job. Let's get into it. All right, so if friction is the villain of our story, how do we fight it? We need something that can get right in between those clashing surfaces and, smooth things over. And that something is a lubricant. It's a great name, actually. It comes from the Latin word lubricus, which just means slippery. And that is its core mission, right? To get between those moving parts, make everything slippery, and just stop those asperities from ever touching in the first place. It's basically the ultimate peacemaker in this tiny, microscopic war. But here's the thing. Lubricants are so much more than just slippery goo. They have a whole range of what you could call superpowers. Yeah, of course, they reduce friction and wear, but they also act as a coolant, carrying away all that dangerous heat. They can form a seal in an engine, which is absolutely critical for maintaining compression so your car doesn't lose power. They prevent rust, and they even clean the machinery by washing away tiny particles of dirt and debris. They're pretty much the Swiss Army knife of mechanical maintenance. And just to see how ridiculously effective they are, we can look at something called the coefficient of friction. It's basically just a number that tells you how much friction there is. Now, without a lubricant, that number is somewhere between 0.5 and 1.5. But look what happens when you add 1. It can plummet all the way down to 0.001. That is a massive difference. That's the difference between a seized engine and a machine that just hums along smoothly. So how in the world do they achieve this incredible drop in friction? Well, it turns out they don't just have one trick up their sleeve. Depending on the conditions, we're talking speed, pressure, temperature, they actually deploy totally different strategies to keep the peace. Okay, so lubricants basically have three main battle plans. First up is hydrodynamic. This is where a nice thick film of oil makes the parts kind of float, so they never even touch. This is perfect for delicate, high-speed machines, think watches or sewing machines. Then you've got boundary lubrication. This happens when the speed is low or the pressure is really high, so the film gets thinner. Here, the lubricant forms this super slippery protective layer right on the metal itself. And finally, for the really tough situations, there's extreme pressure lubrication. This is where special additives in the oil react with the metal to form a tough, solid, sacrificial layer that actually wears away instead of your expensive machine parts. Pretty clever, right? So choosing the right lubricant with the right strategy is obviously critical. You can't just guess. And that's why engineers have developed a whole series of tests to measure a lubricant's key characteristics and figure out exactly how it's going to behave out there in the real world. To really get a feel for a lubricant's true character, we're going to look at three key tests. One for its thickness, another for how stable it is when things heat up, and one to find its absolute breaking points, temperature-wise. First up, and honestly the most important property, is viscosity. The easiest way to think about this is just its thickness. So water has a really low viscosity. It flows super easily. Honey, on the other hand, has a high viscosity. It really resists flowing. And choosing the right viscosity is just crucial. If it's too thin, it won't keep the surfaces apart. But if it's too thick, the engine has to work way too hard just to pump it around. So how do we measure it? Well, one of the classic methods uses an instrument called the Redwood viscometer. And as this quote explains, it's actually pretty straightforward. You just see how long it takes for a set amount of oil, say 50 milliliters, to flow through a standard-sized hole at a very specific temperature. The longer it takes, the higher the viscosity. It's basically a comparative race against the clock.
But here's the catch. Viscosity isn't a fixed number. As any oil heats up, it gets thinner, right? The viscosity index, or VI, is a number that tells us how much it thins out. A really good lubricant needs to be stable and predictable, whether the engine is freezing cold or running crazy hot. So the goal is always a high viscosity index. An oil with a high VI is great because it keeps a stable thickness even as the temperature climbs. But an oil with a low VI? That's bad news. It thins out dramatically, and that can lead to some serious engine damage. That's exactly why high VI oils are absolutely essential for things like aircraft engines, which have to go from sub-zero temperatures way up at altitude to incredibly hot during operation. And finally, we have to know a lubricant's absolute limits. There are 3 key numbers here. The flash point is the temperature where its vapors can briefly flash into a flame. The fire point is a little hotter. That's when it can actually sustain that flame. And then at the other end of the spectrum, you have the pour point. That's the coldest temperature where the oil is still a liquid and can, well, actually pour.
So what do these points really tell us? Essentially, they define the safe operating window for the lubricant. The flash point is your upper safety limit. You need that to be way above the machine's normal running temperature to avoid a fire hazard. The pour point, that's your lower limit. It tells you if the lubricant can even do its job in a freezer or when you're trying to start a jet engine in the Arctic. So when you look at any machine that moves, just remember what's really happening inside. There's this constant, violent struggle going on at a microscopic level. And the thing holding the line, keeping everything cool, and allowing for that smooth, efficient motion are these incredible fluids we call lubricants. They really are the true, unsung heroes of our modern world. So the next time you hear that quiet, smooth hum of a well-running engine, remember that what you're hearing isn't the sound of peace, it's the sound of victory. It's the sound of a microscopic war being decisively won by a very, very slippery hero. And it kind of makes you wonder, what other invisible battles are being fought and won all around us every single day?